Hi, this is Dr. Goldstein, and today I'm going to be talking about the first derivative and how you can use it to sketch the graph of a curve. So for starters, let's suppose that we have a function that's differentiable on an interval. Then the fact that that derivative is greater than 0 on that interval means that your function is increasing on that interval. And to see how exactly this works, if I draw a function that is increasing and I consider what the tangent line looks like, it's going to have a positive slope. Secondly, if my derivative is negative on an interval, that means that my function is decreasing. And I see that if I have a decreasing function and I consider its tangent line, I have a negative slope. And then we see, thirdly, that if a derivative is 0 on an interval, then you know that your function must be constant on that interval. And so for this, I want you to think about this a little bit differently. The derivative being 0, remember the derivative is a measure of the rate of change. So the derivative being 0 means that your function doesn't change. The change of your function is 0. And so if we draw a function that isn't changing, it just has to be straight. It has to be a constant function. Okay, let's look at an example of this and see how we can use that to actually sketch a function. So here is a function that hopefully you look at that and you say, nope, I don't know what that looks like. It is 1/4 x to the 4th minus 2/3 x cubed plus 1/2 x squared. So I'm using the first derivative to sketch the graph. So let's compute the first derivative. So the derivative is going to be 1/4 times 4 is 1. So I get x cubed minus 2/3 times 3 is 2, so minus 2x squared, plus 1/2 times 2 is 1, so plus just x. And I have to say I have chosen this example specifically so that those numbers come out very nicely. And now I look at this and I say, what can I do with that? Well, I could factor it. I could pull an x out of everything. And then I have that quadratic that I could factor into x minus 1 times x minus 1, and I'm going to rewrite that as x times x minus 1 squared. And now the question that I want to ask is, where is this equal to 0? Because this is going to enable me to determine where f prime of x is positive and negative, because 0 is where it can change sign. Because it can change sign where it's 0. It could also change sign where it doesn't exist, but we're dealing with polynomials and they always exist. We don't have that issue here. So we ask, where is this thing equal to 0? And we say, oh, it's equal to 0 when x is 0 and when x is 1. And so we draw a number line, and I'm going to put 0 on it and 1. And I'll color code a little bit. I want to look at the sign of f prime of x, and I know that f prime of x is 0 at 0 and 1. Now, if I plug a number in that is less than 0, let's say that I plug in minus 1 to the derivative, I'm going to have a negative in that x factor, and then I know that that x minus 1 squared is going to be positive. So I know that I'm going to have a negative times a positive, which is negative. Now, if I look at the next two intervals, if I plug in something between 0 and 1 or 1 to infinity, so if I plug in x equals 1/2 or if I plug in x equals 2, I know that that x minus 1 squared is going to be positive because it's squared. I know that it's going to be positive. So all I have to do is look at the sign of the x, and I say, well, it's going to be positive for both of those. So the sign of my first derivative is positive on both of those intervals. Okay, so what this means in terms of our function, and this is what was on the last slide, we see on this interval from minus infinity to 0, the derivative is negative, so my function is decreasing. On the next interval from 0 to 1, the derivative is positive, so my function is increasing. And the same on the next interval, my function is increasing. So what we did here is we found that there are two critical points. Those are the zeros of the first derivative, x equals 0 and x equals 1. And we know that that is where this derivative can change sign. These are where f prime of x might change sign. And so what we've done is we've created a sign chart for our derivative, and we've translated that into what does it mean in terms of our function. So what we know is that f of x is increasing on the intervals from 0 to 1 and from 1 to infinity, and we know that our function is decreasing from minus infinity to 0. Let's look at what this looks like graphically. So there's our function again, and I've graphed it, and I've copied over that sign chart of the derivative and the correspondence between that and the behavior of the function. And so we can see from minus infinity to 0 that our function is decreasing. At x equals 0, it looks like we have this horizontal tangent line where our derivative is 0. And then if we look at what's going on at x equals 1, again, we do have a critical point. So at x equals 1, we once again have this horizontal tangent line. It's not drawn in particularly well there. We have this horizontal tangent line, but on both sides of that, our function is increasing. So the function increases from 0 to 1, instantaneously flattens out, and then continues to increase. Okay, so that is visually what this looks like. Another way of putting this is we notice that at x equals 0, I'm going to erase these tangent lines so that we can see the graph of the function. At x equals 0, we notice that we have what's called a local minimum. That's this visual feature of this graph where we look at it and we say, oh yeah, that's a little dip right there. And we notice that at x equals 1, there's no local extrema. There's no local min or max. And so the first derivative is giving us this information about the visual features of our graph, not just in terms of increasing and decreasing, but another way of phrasing that is in terms of local mins and maxes. So what I'll finish with today is what's called the first derivative test. If we have a critical point x equals c of f, and we know that our function f is continuous and differentiable right around that, if the derivative switches from negative to positive, so I'm reading left to right, negative to positive, then I know that f has a local minimum. And what that looks like is if my graph switches from negative to positive, I know that my function goes from decreasing to increasing, and at this point down here, I have a local min. And this is, again, my derivative goes from decreasing from negative to positive. In B, if f prime switches from positive to negative, then f has a local maximum. So in B, my derivative switches from positive to negative, and at that point I have a local max. This is what this looks like. My graph goes from increasing with a positive first derivative to decreasing with a negative first derivative. C, if my derivative does not change sign, then I do not have a local min or a max. And what that looks like, if my function is increasing the whole time, it's going to look like that. So I still have a horizontal tangent line, but my function is increasing on both sides of that. And if my function is decreasing, this is what that looks like. Again, there is this critical point where I have a horizontal tangent line, but my function is decreasing and continues to decrease on the other side of that. So this is the first derivative test. From the first derivative and determining where it changes sign, we can determine whether we have a local min or a max at any particular critical point.